Okay, so moving on with the topic of prime and composite numbers. We just did the sieve of Eratosthenes to kind of demonstrate a method for kind of using process of elimination to determine what numbers are prime between 1 and some given number. We did from 1 to 100 in that example. Now, one of the most important problems in number theory is developing methods that can take a single number, a natural number, and determine whether it's prime or composite. The sieve of Eratosthenes is nice, for ranges of numbers from 1 to something, but that doesn't really give us a method for taking a single number and saying yes, this is prime, or no, it is not, unless we do the entire process. And on top of that, the sieve of Eratosthenes is only useful for kind of a small range of numbers. 1 to 100 is really not that many numbers in the long run. Some of the things that we use prime numbers for in practice are cryptography, which is kind of like writing codes, or trying to either encode information or decode it or decrypt it is the more correct term there. And those algorithms that use that utilize prime numbers, but to make them work correctly and efficiently, they have to use extremely, extremely large prime numbers. So the sieve of Eratosthenes is not an efficient method for locating prime numbers when we're looking at very large ones. However, we do have these things called divisibility tests, which I sort of alluded to in the previous section, which are a way of taking a look at some particular number and being able to determine very quickly if some other specific number is a factor of that. So to give you an example, it's very, very easy to determine whether or not a number is divisible by 2, because all we have to do there is check if that number is even or not. If a number is even, then it's divisible by 2. If it's odd, then it's not. And it's very, very easy to determine whether or not a number is even. For example, right here, this is the number 2,303,499,298. It's a very big number. However, I know immediately that it's even because the only thing that matters when checking for evenness is the ones place. If it has an 8 in the ones place, it's even, right? In fact, if it has any even number for its ones place, then the whole number is even. That means 0, 2, 4, 6, or 8. And if you didn't know this, the number 0 is an even number. So 2 is an easy number to check to see if it's a factor of something. But actually, there's divisibility rules for a lot of other small, one single digit or even a couple of double digit numbers, and we're going to look at those. So this is our list of divisibility rules. And this is the one that we just talked about. A number is divisible by 2 if the last digit is 0, 2, 4, 6, or 8. That's another way of saying if the number is even. But what are some of the divisibility tests for other numbers? A number is divisible by 3 if the sum of the digits is divisible by 3. This is an interesting one. You take the digits of a number and you add them up. That produces a much smaller number, and then you check if that is divisible by 3. If it is, then the original number was also divisible by 3. A number is divisible by 4 if the last 2 digits is divisible by 4, meaning the 2-digit number at the end. This one we talked about. A number is divisible by 5 if the last digit is either a 0 or a 5. 6 is a factor of a number if the number is divisible by 2 and 6. Notice 6 has 2 and 3. Sorry, I think it said 2 and 6. 2 and 3. 6 has as its factors 2 and 3. In addition, 1 and 6. But 2 and 3 are the prime factors of 6. They are the factors that are also prime numbers. And this is not unique to the number 6. This is a divisibility test that can be used for a lot of composite numbers as well. 7 has a really, really interesting and kind of bizarre divisibility test, and we're not going to use this one. I just put it here in case you're interested, so I'm not going to illustrate it. I'm not going to talk through it, but there does exist a divisibility test for 7. 8, if the last 3 digits are divisible by 8, so the 3-digit number at the end of the number, if that's divisible by 8, then the entire number is. 9 has a divisibility test that's very similar to the one for 3s. If you add up the digits of the number and get something that's divisible by 9, then the original number was divisible by 9. 10, this is one you probably already know. If the last digit of a number is 0, then it's divisible by 10. 11 has another kind of bizarre divisibility test that's kind of similar to the one for 7, and we're not going to use that, but it's just here for reference if you're interested. 12, the last one we care about for now, is divisible, is a factor of a number if that number also has 3 and 4 as its factors. So I want to use these divisibility tests here. We're going to determine which of the numbers 2, 3, 4, 5, 6, 8, 9, 10, or 12 are factors of a particular number. And we're just going to kind of list those. So starting here, is 2 a factor of this number? Well, if it was, then this number would have to be even, and because it ends in a 5, we know that it's not. 3. Is 3 a factor of this number? The divisibility test for 3 says that I add these digits up. So 2 plus 4 plus 4 plus 3 plus 5. Those are the 5 digits of that number. What does that add up to? It's 10 plus 8 is 18. Okay? Well, 18 is divisible by 3. It's 3 times 6. So 3 is one of my factors. Is 4 a factor of this number? Well, the last 2 digits are 35. You just cover everything up except for the last 2 digits. 35 is not divisible by 4. Here's a little tip to help with some of these divisibility tests. If a number is odd, then that means it cannot have any even factors at all. So we've already ruled out 2, but in the process, that actually rules out all other even numbers as a possible factor. So 4 is definitely not going to be a factor. 5, because the number ends in 5, it's a factor. 6, remember we've ruled out all even numbers, so 6 can't be a factor. 8 can't be a factor. Can 9 be a factor? Well, again, 9, the divisibility test is similar for the one for 3s. We add the digits up, which we've already done, and we got 18. Is that divisible by 9? Yes, it is. It's 9 times 2. So 9 is also a factor of this number. 10 and 12, both of those numbers are even, and again, we've ruled those out, so this would be the full list. Notice that we're not including the divisibility tests for 7 or 11. Those are complicated, so we're not doing anything with those in these examples. I want to do the same thing for this one here. 1,335,410 is divisible by 2 because it's even, so I'll list 2. Is it divisible by 3? We have to add the digits up to determine that. 1 plus 3 plus 3 plus 5 plus 4 plus 1 plus 0. What does that equal? So this is 3 plus 3, 6, 7, 12, 13, 17. Okay, 17 is not divisible by 3, so we can rule that out. Is this divisible by 4? For that, I just check the last 2 digits, which makes it 10. 10 is not divisible by 4, so I don't include that. 5, it ends in a 0. Remember, that means it's divisible by 5. 6, it can't be divisible by 6 because the divisibility test for 6 says that the number has to be divisible by both 2 and 3, and we've already said that 3 is not a factor. It needs both of them, and we don't have both of them. Is 8 a factor? We only look at the last 3 digits. 410, you could divide that by 8. In this case, you would get a remainder, so 8 is not a factor. 9, I added up the digits already. I did not get a number divisible by 9, so 9 is not a factor. 10 is a factor because it ends in a 0, so I get a 10 there. 12 is not a factor because we don't have 3 or 4. I would need both of those. So that's my entire list of factors. All right, looking good. All right, so this is the last thing that we want to do here, and I did talk about this a little bit in the first video, the fundamental theorem of arithmetic. In order to understand the fundamental theorem of arithmetic, we need to talk about prime factorizations. So we've talked about factorizations, and we've done a couple of examples where we found them. Remember, a natural number can be represented as a factorization if you write it as a product of 2 or more of its factors. And one thing we stated early on in this section is that factorizations are not unique. Because a given natural number can have several different ways of writing it as several different ways of writing factorizations. But that's only for a general factorization. If you specifically try to find a factorization of a number where all of the factors are prime numbers, then that's what we call a prime factorization. And the fundamental theorem of arithmetic, a theorem is a fact in math that has been proven. The fundamental theorem of arithmetic that says that every natural number greater than 1 has only one prime factorization. They always have exactly one, as long as we're not considering rearranging those same factors different. So I'm going to show you how to come up with a prime factorization for a number, and then we'll kind of reference the fundamental theorem of arithmetic in that process. The trick is to use something that we call a factor tree. So I want to find prime factorizations for each of these two numbers, 550 and 144. And what we do is we create what's called a factor tree. What I'm trying to do is find two numbers that can be multiplied together to make 550. There's several different things I could come up with, but what comes to mind for me is the fact that this ends in a 0 means it's divisible by 10. Remember those divisibility tests. 10 times what makes 550? Well, dividing a number by 10 is just cutting that 0 off. So 55 times 10 makes 550. Now, there's other options I could have used here. I could have looked at this and said, oh, that's an even number. I could divide it by 2, and then think 2 times what is 550. So notice your factor tree may not look exactly like mine. But because of the fundamental theorem of arithmetic, no matter how you start your factor tree, you will always end in the same place, and that's the important part. So what I'm going to do is continue breaking these numbers down. Neither of these are prime numbers because both of them are divisible by 5. I can see this ends in a 5 and that ends in a 0. So we continue breaking these factors down into products of two more factors. 10 is equal to 2 times 5. Now we know from doing the sieve of Eratosthenes earlier, 2 and 5 are both prime numbers, and once I reach prime numbers, I circle those. What about 55? 55 is equal to 5 times 11, and we know that those are both prime numbers as well. Okay, so now down to the prime factorization. I want to take the number 550 and write it as a factorization in which all of the factors are prime numbers. Well, in order to do that, I would just use all of the prime numbers that I have circled here. And what I tend to do, this is common, is I don't write them necessarily in the order that I've written them here. I write them in order from smallest to biggest. So I have a 2. That's my first prime factor. Times, now my next largest prime factors are these 5s here. I could write 2 times 5 times 5, but because I have two 5s, let's write it as 5 squared instead. And then finally I have that 11 there. This is the prime factorization for 550. Now I say the because the fundamental theorem of arithmetic says that there is no other product of prime numbers that could ever equal 550. These are the only ones. And up here where I say not counting rearrangements of factors, notice I could have written this as 2 times 5 times 5 times 11. I could have written it as 11 times 5 times 5 times 2. I could have written 5 times 2 times 5 times 11. I could rearrange these factors in any number of ways, but I'm not considering those rearrangements to be any different. So that's important because otherwise, the fundamental theorem of arithmetic wouldn't be true. Let's do this one more time. 144. 144 is a perfect square. I recognize that as 12 times 12. 12 can be broken down in a number of ways. I'm thinking 3 times 4. 3 times 4. Now, 3 is a prime number. I know that to be true. 4 is not a prime number. It's equal to 2 times 2. And so I end up with a lot of 2's, all of which are prime. Once you've circled, once you have no more, uncircled numbers, I should say, that can be broken down any further, that's how you know that your factor tree is done. Now look at my factors. 144 is equal to what? I have 4 2's here, so I'm going to write that as 2 to the 4th power. And then I have 2 3's here. I can write that as 3 squared. So these are the prime factorizations that I'm looking for. Okay, and that's going to wrap it up for 5.1.